Are you guys able to see it?
Yeah, perfect.
Okay, so I might have to do some back and forth for the tutorials, but we'll try and make it work. So yeah, welcome everyone to today's session about practical NLP. I'll be doing some hands-on and some concepts around what NLP is, and also there'll be some case study focused discussions around how you can apply NLP based on some of my past experiences in the industry. So briefly, let me talk about today's agenda. Let's see. Yeah. So a brief intro, and then we'll focus on what is natural language, what is NLP, why do we need NLP in the first place, some popular NLP applications or use cases of how NLP can be used to solve different problems, standard NLP workflow which you can use to tackle problems, typically any type of problem which NLP can solve, some hands-on demos based on 2 case studies which we will be talking about, and then some industry case studies around problems I've solved in the past. So brief intro, basically, as Ankita already introduced me, I'm a data scientist working at Red Hat, and besides that, I've also consulted with several startups and other companies like Springboard, and I'm also an editor at a popular online data science publication towards data science. I write articles, books, papers. I love publishing my work online and even open source my stuff on GitHub, so feel free to check it out. And yep, that's about me. Let's get started. So for NLP, we need to understand what is really natural language in the first place. So what is natural language? Well, like we communicate between each other, right? So humans communicate with each other using natural language. So basically, it's a method or a mechanism using which we communicate with each other. And now even machines, right? Like things like speech to text or text to speech. It is very different from, let's say, a constructed or a language like a programming language, because there is grammatical constructs, there is syntax, there is semantics, so many things. Besides that, it's also highly unstructured in nature, because like you have structured data in relational databases, as you know, speech or text data, pretty much unstructured. Hence, it's very difficult to parse and comprehend by machines. So the idea now is, as text data is unstructured and available in so many different formats, be it documents, emails, messages, so on and so forth, how do you parse this data and how do you try to extract meaningful insights from it? So that is where natural language processing comes in. So what is NLP? NLP is basically, you can think of it as a field which is at the intersection of several other major fields, including computer science, artificial intelligence, and linguistics. In a nutshell, NLP is basically applied linguistics, where you take in conceptual aspects around how do you interact between humans and computers based on the language which we speak, and how do you basically program computers to kind of comprehend that unstructured natural language, right? Like, how do you process that language? How do you analyze it? How do you understand it? And finally, how do you build models on it so that you can get further insights in the future, or basically predict stuff? So you may hear about different terms like text analytics, text mining, NLP, and so on. Basically, they are kind of the same thing. The idea is it's applied linguistics, where we are trying to automate things like how do you comprehend text data, how do you apply different types of statistical or machine learning techniques to extract specific patterns, topics, concepts, and kind of transform this unstructured, noisy text data into meaningful insights, just like we do for any data science problem at the end of the day. So why do we need natural language processing really? Well, the motivation for NLP is that, as you know, typically in any enterprise, we have worked with a lot of relational databases, right? Like SQL databases and data warehouses and so on. Now, the idea here is the data here is very structured, it has strong relationships, and it is kind of easy to mine for patterns and analyze it because your data is structured. It is more or less clean because you have your ETL pipelines running in day in and day out and so on. But the main problem here is that a lot of your data in the enterprise is potentially unstructured text data in the form of, let's say, files, documents, even let's say logs and so on. And based on different statistics, it has been seen that almost 80% of enterprise data is available in unstructured text formats. And basically, since it's tough to parse it, it's tough to process it, it's tough to analyze and get meaningful insights from it, basically a vast potential is still untapped with regard to text data in the enterprise. And that is where NLP is coming in with the promise of, can you generate insights which you were never able to kind of generate before with only structured text data? And as I said, 80% of any data typically in any enterprise is pretty much unstructured or semi-structured, just like log files, documents, messages, blogs, tweets, social media, call center records. And the idea is, how do you basically get all this data, process it, and try to mine for useful insights? And that is what we will be talking about with regard to potential standard workflows which you can use in the industry. And another reason for the motivation for NLP is, as you know, that there has been a lot of hype with regard to image data, right? Like you have convolution neural networks, which are doing a lot of stuff like motion detection, object detection, semantic segmentation, image classification, and so on. But realistically, if you think about it from an industry perspective, unless you're working in a very specific sector, like let's say a computer vision based company, or let's say a healthcare company, honestly, when was the last time you had to do things like detect stop signs at work, or let's say find out the total number of vehicles on the road, right? As compared to this, think about things like, can you analyze your log files? Can you improve your operational analytics, basically known as AI ops? Can you mine for insights from all the text data you have? So that's the thing, right? In major industries across the world, text data is more prevalent than, let's say, a niche domain like computer vision. And a lot of useful data is text, like we discussed. You have public data in the form of tweets, news, blogs, Reddit. You have proprietary data from your own databases, logs, documents. And also you have things like survey data, which may be public, which may be private. Things like measuring net promoter index surveys and so on. You can do a lot of stuff like sentiment analysis, causal analysis, and so on. And obviously, NLP models are realistic and affordable. You don't have to spend a lot of money. A lot of the frameworks are open source, and you can deploy them easily using the right deployment frameworks, be it you want to deploy it using a container, be it you want to just deploy it as a standalone web service, and so on. So let's talk about some of the important NLP applications in the industry these days, based from a technical perspective and also a practical perspective. So some of the popular applications include, obviously, the most popular one, sentiment or emotion analysis, very useful for survey data, very useful for data like reviews and so on, understanding your customer feedback, understanding how employees feel. So you can use it in diverse sectors, be it in HR, be it in, let's say, survey data, review data, and so on. Then you have information extraction, pretty much used a lot to extract and mine for patterns like relationships, right? Who is related to whom, what is the relationship, and so on. Used a lot with regard to knowledge graphs, which is coming up and becoming really popular these days. Obviously, it's not a new concept. We had concepts like semantic web since a long time, but knowledge graphs are becoming more and more popular these days. And then obviously one of the most popular case studies around the world is search engines, right? Like Google, which we use day in and day out. Can you rank and show the most relevant documents based on the search query you're entering in free-form text, right? That is natural language. So information retrieval, search engines, ranking of documents, search relevancy, pretty much very popular applications in NLP. And then you have things like a machine translation, where you're translating, let's say, speech to text or text to speech, or even translating different languages, right? So sequence to sequence models like encoder decoder models have become really popular these days to translate data from one language to another language. And obviously other mainstream tasks like question answering, chatbots, and so on are gaining more and more prominence. And I don't know if this is clear, but we'll talk about some of the most popular use cases pretty soon. But as you can see, the number of things to be solved with NLP is pretty vast. You have things like document classification, standardization, entity extraction, tagging, named entity recognition, parts of speech tagging, parsing, sentiment analysis, document summarization, document clustering, ranking. Basically, the possibilities are endless, and you can apply different types of techniques and solve different types of use cases across diverse domains in the industry. No matter which industry you're in, if you have text data, a lot of these use cases will be relevant for you to gain, I would say, useful insights. So I would say these are some of the most popular and common NLP use cases, which you can call as realistic or let's say practical applications which can really benefit your organization depending on the type of data you have. One is text classification, obviously, where you categorize data into discrete categories. Things like support ticket classification, news article categorization, pretty much are examples which fall under this category. And then you have things like text clustering and similarity, where we have aspects like recommender systems, content-based recommender systems. We'll look at an example later on where based on text descriptions, can you recommend similar items? Or can you recommend things like similar movies to the user? And then there was an interesting use case which we solved where we found out duplicate knowledge articles with fuzzy matching. So leveraging features from text data and trying to find out what is the most similar entity to whatever we are trying to match with. And then obviously, like I mentioned, searching, ranking, and information retrieval, where you are trying to showcase the most relevant documents based on some query which the user is entering. And other aspects like parsing and named entity recognition, very useful to get entities from legal documents, from contracts, from healthcare records, in an automated fashion instead of you manually parsing through documents and labeling data or trying to extract entities from hundreds or thousands of documents. And obviously, then you have text summarization, where you're trying to summarize entire documents and provide a neat and concise summary, just like, let's say, an elevator pitch, right, where you have less than a minute to pitch about your startup or whatever you want to call it. And then you have topic models also, where you can kind of find out major themes which are occurring across different documents in your corpus. A corpus, by the way, is a collection of documents. That is the general terminology in natural language processing. And we pretty much talked about machine translation, right, where you translate from speech to text or text to speech or translate across different languages. And some of the things which are gaining popularity these days are conversational interfaces like chatbots, where you can type in your query and get some relevant answer or do some potential action based on that. Personal assistants, right? Like you just talk or say some commands and they will do that task for you. And obviously, sentiment analysis is one of the most practical use cases to really analyze your survey results and correlate some causal analysis with your net promoter index scores, right? Like why are employees happy or sad? What is the reason behind that? So on and so forth. So what is a standard natural language processing workflow you can kind of follow for any mainstream project, let's say, which you want to take with regard to NLP? So this is the general workflow which I follow. And this is pretty much a standard based on the CRISP DM model, which many of you might be familiar with, right? The cross-industry standard process for data mining. So obviously, some of the steps are not shown here, which is non-technical, like the business understanding the use case, what you have to solve, and how do you translate the business problem to a machine learning or let's say a data science problem. But let's say once you have that figured out, the next point would be obviously getting the data, right? The data understanding. And in this case, pretty much you would be having text documents. And what do you do with these text documents, right? So obviously, text data is unstructured, right? And it might be potentially very noisy. The first step usually is to clean this noise, to wrangle the text data, to pre-process the text data. So text pre-processing is pretty much the first step, where we do different things like removing stop words, removing potential noise from the data like HTML tags, and so on. We'll cover this briefly in the next step. So potentially the next stage is text parsing. Like if you want to extract potential named entities, or if you want to parse and find out the potential parts of speech to be used as features in the future, then you would be parsing your text data and kind of do some basic exploratory data analysis, like what are the top phrases which are occurring, or what are the top words which are occurring? Do we need to extract out some custom stop words which potentially don't have any meaning? Like let's say if I'm working in the service management based data, I would have words like issue, problem, and so on, which are potentially words which will be occurring across all the documents. So they wouldn't be carrying much meaning overall. And those are known as, let's say, custom stop words. So once you have your data cleaned, what would be the next step? So machine learning or deep learning algorithms, as you may know, while they are pretty powerful, their major limitation is they can only work off matrices of numbers or vectors of numbers and so on, right? You can't just feed in some text data to any model and it'll start doing stuff for you. So the next step would basically be the feature engineering step, where we are trying to represent the text data into some numerical format which can be consumed by downstream machine learning or deep learning models. So it's not just like you just take the text and convert it to any random numbers. Obviously, you have to follow some models, typically known as the vector space models. And we'll be covering this briefly also once we go to the next stage. And once you have your features, let's say, which are potentially things like the number of times words are occurring across different documents, or more advanced concepts like word embeddings, where you have vectors of numbers for each word. What you would do next is obviously kind of crystallize the task you want to do, whether you want to classify the text data, whether you want to cluster the text data, whether you want to find out potential similar documents, or whether you want to rank documents for search and so on, right? So that is the modeling phase or the pattern mining phase, where we try to build machine learning or deep learning models on our features from the text data, or we want to find out potential patterns from our text features. So once we build these models, the next step would obviously be evaluating the performance of the model, right? Like if you're using a classification model, you can use things like precision, recall, accuracy, which kind of talk about how accurate the model is when it's making predictions, how many samples it is able to predict, how correct are its predictions, right, and so on. So that is where you basically evaluate the performance of your models. And obviously, if the performance is satisfactory and the end user, or let's say your stakeholders, are happy with it, you then go ahead and deploy your model. So typically, this is the standard NLP workflow, which can be used to solve most NLP problems. Obviously, there may be slight variations depending on the use case. So what are the potential steps for text wrangling or pre-processing? Basically, there are aspects like removing HTML tags, right? Like if you're scraping data from the web, you may end up with tags like the paragraph tags, tables, and so on and so forth, div tags. So you might need to remove these HTML tags because they don't really carry much information which can help you build a useful model. Other than that, there are standard stuff like removing extra white space, removing new lines, carriage returns, removing special characters and symbols, right? Like let's say symbols like exclamation mark or the pound symbol, ampersand, whatever be it. You don't really need these symbols unless it is very contextual. So you would be removing these things. And often you may not need numbers also. You might just want to focus on the core text data, right? Like the alphabet. So you might need to optionally remove numbers in many cases. And if you're dealing with data from different languages, like specifically European languages, some of the alphabets might have an accent. And to remove those accents, you would need to convert it to ASCII characters, where basically alphabets from A to Z are kind of what we are looking at as the main outcome. So if you have an accented A, it'll be converted to a normal A, so on and so forth. Then there are some other advanced, I would say, text wrangling techniques like stemming or lemmatization, where stemming is basically converting a word to its root form known as the root stem. But this root form may not be a semantically correct word. Like, let's say if you have the word lazy or lazing, if you convert it back, L-A-Z-I-N-G may be converted to L-A-Z-I, because let's say that is the root stem. But it's not a semantically correct word. That is where lemmatization comes into the picture, where it tries to convert any word to its base form, and that base form is always a dictionary correct word. So in this case, L-A-Z-I-N-G would be converted to L-A-Z-Y. So the idea is, if there are different forms of a word like running, runs, run, ran, can you convert it to a standard format like RUN, the base form? That's why we do that, so that we can remove more of the variation for the same topic or the same word. We talked about stop words briefly. So stop words are basically words which have little or no meaning. Things like filler words, articles, the, and, or conjunctions, prepositions, pronouns like he, she. Usually they don't really carry much meaning, so you can potentially remove these words. And sometimes you might need to tokenize your text depending on what you're doing, like parts of speech or so on. Then you can use that optionally. And other optional steps can include improving the grammar of your text data, correcting the spellings of your text data, and so on. These are potentially more computationally expensive tasks. So once we do the text wrangling, the next step would potentially be feature engineering. Just give me a second. So in feature engineering, we are basically trying to convert the pre-processed and cleaned text data into some effective numeric representation, right? Because downstream machine learning models or deep learning models can't really work on unstructured text data like we discussed before. So this diagram pretty much sums up what we want to do. We have the clean text data. We want to convert it to an effective numeric representation, typically known as vectorization, where we convert the text data into vectors. So like I mentioned, basically ML or DL models at heart are math-based models, and they can't understand unstructured text data. So there are different schemes or models which we can use, which fall under the umbrella of vector space models, because we are transforming the unstructured text into potential vectors, and all the vectors together make up your vector space. So there are different techniques, as you can see: bag of words, term frequency, inverse document frequency, topic models, similarity-based features, and more advanced deep learning model-based features like word embeddings, pretty much things like word2vec, glove, fast text, and so on, which can be used to extract, I would say, numeric vectors from our unstructured text data. So we'll try and go to the hands-on tutorial once we finish some of the main aspects here. So traditional text representation models include bag of words, bag of n-grams, the TF-IDF model, and the document similarity model, where you can extract potential features like the number of times each word is occurring across every document, the number of times, let's say, specific phrases known as bigrams or trigrams are occurring across all the documents. You can also normalize these weights using a scheme known as term frequency, inverse document frequency. And you can also compute pairwise similarity between documents and use those as features, which we will be using when we build our movie recommender application. So going to the next part, which would be the deep learning models. So deep learning models have been, I would say it has been quite a while, but more recent than the traditional statistical models, where we have models like word2vec, glove, and fast text, which try to take into account the sequence of words, the ordering of the words, the context across different words, which words are occurring closer to each other and so on, and try to give us dense embeddings, which is just a fancy name for a fixed width vector. So once you do feature engineering and once you have the feature vectors, these are some of the downstream machine learning or deep learning tasks you can do after feature engineering, right? Like you can classify text data, you can build recommendation systems, you can cluster, you can build topic models, you can analyze the sentiment, you can do semantic analysis, like find out potential relationships across different entities in your data. The challenges in the industry is not specific to implementing text classification or clustering, but like I said, converting or framing your business problem and translating that to a specific machine learning task or a data science task, right? So no one will be telling you, here are some documents, can you run a random forest model and do some text classification? They will be giving you an ambiguous problem, like let's say they want to analyze the cause of your net promoter index going down from 90% to 78%. And it would be up to you to figure out what kind of data you want to get. What is the task you want to use there? Do you want to do sentiment analysis there? Do you want to correlate the sentiment with the net promoter index score and so on? So the idea here is you need to use your analytical thinking and let's say your expertise to kind of frame the task as whether you need to do classification, clustering, topic modeling, summarization, and so on. And obviously, if you check out Kaggle or potentially any tutorials on the web, most of them will stop by saying that our model got X% accuracy. But that is not where your journey stops, right? Because you folks are practitioners, let's say, who may want to implement these things for your company or for your clients or stakeholders. So you would have to think about other aspects like which model is more computationally expensive, which model can be easy to deploy, what is the latency of your predictions, do you need to build an end-to-end data transformation pipeline, how do you pass new data into your previously trained model, how do you update a trained model, how do you deploy it? So all of these things you have to think about when you are working in the industry, and these are the things which are not covered in so much extent, let's say in academia or tutorials or competitive websites like Kaggle. And the challenge with machine learning or deep learning models is it is very experimental, it is very iterative. So unless you really try it out, you will not know how good or how bad the performance is. So we'll be covering two hands-on demos today. Before that, I would like to briefly showcase a couple of things which I talked about previously, like text wrangling, feature engineering using the vector space models, and then we'll move on to the hands-on demos and finally close it out with the industry use cases. So just give me a second. Is this visible? Can you see it clearly?
Yes, Dipanjan, it's all good. It's visible.
Great. So these are some standard techniques for text wrangling, which is our first tutorial. We'll go through this briefly. Now, all of this code is available in my GitHub. Feel free to check it out anytime. The intent here is not to like memorize or understand each and every line, but kind of get a high-level overview of what are the things you can do and how do you do it typically. All of these are using open source libraries and Python, so it's pretty much out there. So some of the most common things to start with when we are cleaning text data is obviously case conversion, right? We want to convert text to, let's say, lowercase or uppercase or title case and so on. Typically, we would be converting it to lowercase usually to standardize it. And then there is tokenization. Like if you have a big paragraph of data just like this, let's say, the first thing you can do is tokenize it into different sentences. As you can see here, it's comma separated, which means our list of data is having different sentences, which it has identified from the corpus. And we are using the natural language toolkit here, the NLTK library, which is pretty much open source. So you can tokenize a paragraph or a document into different sentences, and then you can even tokenize each sentence into words, as you can see here. And obviously there are other open source libraries also like Spacey, which can help you do the same thing, as you can see, give you the sentences, give you the words and so on, which you can use. And as I was saying, if you're working with data from potential websites using web scraping or crawling and so on, you might end up having data like this. As you can see, we have things like the paragraph IDs, ampersand signs, and so on. These are the HTML tags, CSS, and so on, which we don't really need. We just want the text data. So you can use a simple function using the open source library Beautiful Soup to just get the text data and remove the unnecessary HTML characters. And as you can see from this really noisy web page, we are extracting the core text data. And obviously, we have used things like regular expressions to remove new lines and potential extra white spaces and so on. So the accented characters, if you remember, I had talked about. So this is exactly what it is. There are some letters which have an accent, typically using a specific symbol on top of it. And if you don't normalize this, the word will be treated as a different word from, let's say, the actual word without any accent. So we can use the Unicode data library to normalize these accented characters and get the output as standard ASCII English characters. And then obviously you may have things like special characters, symbols, emojis, as you can see here with the smiley face. So you can use regular expressions to keep the numbers or not keep the numbers and just keep the text also if needed. As you can see here, if I remove the digits, it removes it. And if I want to keep it, it'll potentially keep it. So that is what the function is doing. Remove digits is an optional argument, I would say. And if I want to remove the digits, potentially I will just keep the text data, basically alphabets. And if I want to keep the digits, I'll keep all the digits, basically something between 0 to 9. That is how we write the regular expression. And we remove everything else. Contractions is also an important part, which I didn't talk about earlier. So there are words like isn't, don't, and so on, which you can expand to do not, is not, and so on. And that helps you standardize your text data again. Else you'll have to deal with, again, the apostrophe symbol separately. So as you can see here, if I have this text with a lot of contractions, right, with abbreviated text like I, y'all, can't, and so on, it basically expands it to their full form. And this helps you normalize your text data. The contractions library, by the way, is also open source, and I also have the same version in my GitHub repository, where internally it is, again, just using regular expressions, looking up at a dictionary, as you can see, like if it finds a match for ain't, it'll convert it to is not, and so on. So we talked about stemming previously, right, where we want to convert the, I would say, inflected form of a word, like different variations of the word, to its root stem. So as you can see here, jumping, jumps, jumped, it converted it correctly to jump. But the word strange, it converted it to strang, which is not a dictionary correct word. So that is where lemmatization comes into the picture. Obviously, there are different types of stemmers, like this is the Porter stemmer, you have the Lancaster stemmer. Some of them have different variations, but these are all based on fixed rules. Like typically it uses if-else rules to give you the root stem. And in lemmatization, what happens is it tries to convert the word to its base form. So running or ate, it converts to run or eat, saddest to sad, fancier to fancy. So it potentially does a dictionary lookup, and you always have to give the parts of speech for it, else it'll not work correctly. And hence it's more computationally expensive because it always does a dictionary lookup. And stop word removal, right? So potential stop words, just like I said, I, me, myself, we, are, pronouns, articles, and so on. So if you have a sentence, the brown foxes are quick, they are jumping over the sleeping lazy dogs. If you remove the stop words, so stop words can be available from NLTK using a standard English stop word list, and you can even supply your own custom stop words. So here, as you can see, all the stop words like the, are, and everything has been removed. And let's say if I want to add custom stop words, I just add the words to my custom list, stop_words. And now it even removes words like brown, which potentially is not an English stop word, but if you want it to be, we can always make it. And it just does a simple token matching. So a sentence is just converted into tokens, and then it basically removes it if it finds a match in a stop word list. So let's move on briefly to feature engineering. Basically where we convert text to some numeric representation, right? So as you can see here, we have different sentences here, or let's say these are different documents. So the simplest model is the bag of words model. Before that, we do some simple text preprocessing, like lowercasing it and removing the special characters, removing the symbols, removing spaces, and so on. And this is our normalized, let's say, corpus of text documents. So the bag of words model basically converts our text data into a matrix where each column is potentially a unique word across our corpus of documents, and the value is the number of times that word is occurring across each document. So since I have 8 documents, I have 8 rows here from 0 to 7, and like the first document was beautiful blue sky. So as you can see, beautiful is 1, blue is 1, and sky is 1. So potentially just showcasing the number of times each word is occurring across the document. This is one way of representing it. Another way is where you also try to find out potential phrases, like how many times beautiful sky is occurring, or how many times blue and beautiful is occurring together, and so on. The TF-IDF model is where we normalize these term frequencies, which you just saw here, these counts, by the number of times that word is occurring across all the documents. So let's say the word blue is occurring across all the documents. Potentially, it's not really useful to any model because that word is occurring everywhere. So you try to normalize the number of times that word is occurring by dividing in each document with the inverse document frequency, which is potentially the number of times that word is occurring across your complete corpus. So obviously, if you have n documents and it's occurring in n all of them, your weights will be reduced to almost 0. And then you have document similarity, where we can use some math measures like the cosine distance to potentially find out how similar each document is to all the other documents. And obviously, each document is completely similar to itself. So the diagonal, you can safely ignore it. It'll always be 1. Our main point of interest is how similar each document is with the others. And you can use things like clustering to potentially find out which documents can be grouped together using features like all of the above, be it the similarity-based features, TF-IDF, bag of words, and so on. We'll go through this briefly, considering the time we have, and also since we want to talk about some actual use cases. So the limitations of the bag of words model is that it completely loses the sequence of the words, the ordering of the words, the context, and so on, right? Because we are just finding out the number of times each word is occurring. We lose the ordering, the context, and so on. That is where we have the newer deep learning models, which take into account all of the limitations which the bag of words based models have. So using the same document again, you can pre-process your text data, and then you can use a model like the word2vec model, where potentially it has 2 variations, the continuous bag of words or the skip-gram model. So the continuous bag of words model is like, given that we know all the surrounding words, can we predict what the center word is? And the skip-gram model is, given that we know what the center word is, can we predict what are the surrounding words? So GenSim is an open source framework from which you can use the word2vec model. You just clean your text data and you train your model you can specify the scheme you want, whether you want the skipgram model or whether you want the continuous bag of words model, what is the context window you want to take into account, and so on. And once you train the model, you can visualize the embeddings. So what is an embedding really? An embedding is just a fixed length vector. So as you can see here, the word sky is a vector of size 15. And why is it 15? Because when we train the model, we set the feature size, we set it to be 15 explicitly. So you can set this to anything, 300, 100, and so on. Think of it like a hyperparameter for a machine learning model. And as you can see here, the word2vec model has kind of figured out the context of which words are occurring close to each other. Like you can see the quick brown fox jumping over the lazy dog, all these words are occurring close, and things like the weather, sky, color of the sky occurring closer to each other, and items related to food and breakfast occurring closer to each other. So that is the beauty of the word embedding models. They can understand the context of the words, and that helps you to preserve the semantic meaning of the words, not just view it as raw counts. So we'll briefly go through 2 demos and then close it up with some industry use cases. So one is a movie recommender system. Given a whole database of movies and their descriptions, can we use natural language processing to recommend similar movies to users based on the movie and a description of their choice? And the second one is, given an e-commerce store with various products for which people have written reviews, can you predict the potential rating they have given for that product? So for the movie recommender system, this is the workflow, pretty much in line with a standard workflow. You get the data, you clean the movie descriptions, you build TF-IDF features based on the bag of words model, you compute the document similarity based features, right? Like how similar one movie description is to another. And then given some movie, you recommend similar movies based on the movie description. And for the product rating prediction system, again, a similar workflow. You get the e-commerce review ratings data set. You do data pre-processing on the review data, which is basically our text reviews. You try different types of features here, like number of times each word is occurring, number of times capital letters are occurring, small letters are occurring, symbols are occurring, parts of speech, number of times nouns are occurring, adjectives are occurring, sentiment of the text data, and you try to predict the rating using different types of classification models. And basically the same process as a CRISP DM model. We train, we evaluate our models, and we reiterate. We'll quickly go through these 2 tutorials. These are available again on GitHub, so feel free to check it out and even try it out on your own. So we are dealing with the TMDB movie database. As you can see, this is our data. We have details pertaining to each movie. The main thing which we really need to focus on is our overview, the title of the movie. So this is our main area of interest, right? What is the title of the movie? As you can see, what was the tagline of the movie, the overview of the movie, a brief summary, you can think about it like that, and the description of the movie, a detailed description. So the first step is simple text pre-processing, where we get in our text data, we lowercase it, we remove the spaces, we tokenize it, we remove the potential stop words, and we get the normalized text data, just like any other workflow. And then the next thing is we extract the TF-IDF features, where we convert each pre-processed movie review into a TF-IDF vector based on the bag of words model. And then we find out how similar each movie description is to the other movies. As you can see, movies 0 and 1 are not at all similar, only 0.01, around 1% similarity. So once we have this similarity matrix, think about it this way. If we query for a particular movie, we can sort by the similarity results of the other movies and show the most relevant movies. So basically here we kind of get some popular movies like Interstellar, Deadpool, Jurassic World, Pirates of the Caribbean, and so on. And how do we find out the similar movie? we basically find out which position the movie Minions is located. We get the similarity vector, right? Like how similar all the other movies are to this movie Minions. And then we sort it. And we find out that these are the top 5 movies which are most similar to the Minions movie based on the similarity features, document similarity features. And as you can see, Despicable Me 2, Despicable Me, pretty much in the same series, right, as Minions are showing up. And then you can build a pipeline around this pretty much by plugging in each movie, getting the document similarity vector, sorting the similarities, and showing the top 5 movies. So as you can see, for Interstellar, it is kind of recommending space-related movies. Guardians of the Galaxy. For Jurassic World, all the other Jurassic Park movies, as you can see. Pirates of the Caribbean, all the other Pirates of the Caribbean movies. Same with Captain America. It's even recommending Avengers, right? Captain America, the Winter Soldier. So basically, the idea here is using simple features like document similarity, where you measure how similar one text document is to another. You can build a content-based recommender system. And this is basically a second case study where we have our reviews which customers are writing and they are rating products. So using that historical data, given a new review, can we predict what should be the rating for it? So our potential data set is this, as you can see. We have a review and we have a rating of whether they like the product or they didn't like it. It's very similar to sentiment analysis. So obviously, some of the workflows are very standard to machine learning, like building a training data set and a test data set, typically where you train the model and you test it, the performance on the test data set. So there are different features which you can build because, as you know, feature engineering is very crucial to any machine learning or deep learning workflow. So the first set of features which we do are pretty simple. We just find out how many characters are occurring across the reviews, how many words are there, what is the word density, which is potentially the character count divided by the number of words, right? That is what we are doing. We are also finding out the number of punctuations which are occurring, number of title words, uppercase words, and so on. Basically numeric features which can help the machine learning model. Then we build a simple logistic regression model on this. And as you can see, it is not even able to predict any of the products which are not really likable to the customer. So what do we do next? We try to improve the features. We try to find out the number of nouns which are occurring, the number of verbs, adjectives, adverbs, pronouns, and so on. And that is what we do using parts of speech. So these are potential parts of speech tags. And you can use these to find out the nouns, pronouns, verbs, adjectives, and adverbs, and the number of times they are occurring. So as you can see, we have all these features now, number of nouns, verbs, adjectives, and so on. And we rebuild the model. So it looks like it has improved slightly, and it's able to predict around 5% of the negative reviews now. And F1 score is around 0.1% actually, around 10% you can say for the negative reviews, which is pretty bad. So since we are dealing with reviews, text sentiment might be a very useful feature where we try to find out whether the polarity, basically the score, is positive or negative. So it's typically in a range between -1 to 1, a normalized range. If the review is really negative, then it's -1, and if it's really positive, it's 1. And you can also get the subjectivity, like how much of emotion is expressed by the person who's reviewing it. So 1 means like they are expressing a lot of emotion, and 0 means it's just a general statement. They are not really expressing emotion. Just like this. I really hated this ugly t-shirt. Polarity, as you can see, 0.95 minus 0.95. And this is an amazing pair of jeans. Polarity is 0.75. So that is how you get the scores. We use the text blob library here. And based on all these features now, we see our model has improved, right? Our previous F1 score was 10%, now it's 43%, and recall from 5%, it's 32%. So what we do next is we do some standard pre-processing techniques, which we discussed before, cleaning the text data. And then we add the bag of words-based models, right? Like the number of times each word is occurring across all the reviews. We add in those features also, and then we rebuild our model. And as you can see now, our overall F1 score has become close to 90%. And we are able to predict 74% of an F1 score, which is a harmonic mean of the precision and recall. So almost 70% of our negative reviews, we are able to predict. And our precision is 80% there, which means out of all the times we are predicting a product is negative, we are actually correct 79% of the time, which is pretty good. And obviously for the positive products, it is high because the number of samples is also higher. So this gives you an idea of how you can extract different types of features like count-based features, parts of speech, sentiment, and so on using potential open source libraries, and keep iterating multiple times and basically build the best model. And to wrap it up with some industry case studies which I've solved in the past. So potentially one of them was from IT service management, where you have aspects like knowledge management, incident management, where you're trying to, let's say, reduce the number of tickets different services have in your organization, right? Incident management is one of the key processes in service management. The goal of incident management at the end of the day is to reduce incidents as much as possible and resolve them as quickly as possible so that your business impact is minimal. That's the main thing. So what are the AI-based use cases which you can solve here? One is automated incident priority categorization. Whether a ticket should be of high priority, medium, or low, you can automatically classify it using text classification based on historical data. Another one is what is the root cause of the incident. If you have incident specialists who are labeling the root cause day in and day out manually, which we had in our case, we built a machine learning model which was able to predict with almost 80 to 85% accuracy what should be the root cause. And obviously we had a lot of root causes with different distributions of data. Another thing is if you potentially know about incident management, once you have an incident or a problem, typically you use a knowledge article or a solution to close it. So if you have enough historical data, can you automatically solve the ticket itself and close the ticket? Right. So let's say if there is some server issue, if you already know from the historical data that this was the script used to solve it, can you just trigger it and fix the issue instead of someone spending hours to go through all the other tickets, then coming to that and solve it? So basically it reduces your service level agreement times. And other aspects are like, can you showcase key themes of daily incidents? That is more around exploratory data analysis. So predicting incidents with root cause and priority. Enterprise services typically have their own operations team, right, who manually classify and tag and label the root cause and the priority of potential tickets daily or weekly. So the idea is based on historical data. Can you model and build a classification model on this data to predict root cause and priority for future tickets based on past historical data? Obviously, herein comes the opportunity for NLP and machine learning or deep learning to be combined and do this. How do you do that? You leverage, again, you start with the data, right? You get the historical ticket data. You should have the categorized root causes or obviously the priority, which obviously should be there given that these were valid tickets in your organization. You pass and process the ticket descriptions like the issue description, the short description, long description, other structured fields, maybe like what was the product, what was the location, and so on. And you generate text features then, like bag of words, embeddings, and so on. And once you have the numeric features, you just go for building classification models. And as you can see here, these are some sample tickets and root causes, right? Like Outlook not working, Let's Meet plugin disabled, sync issue, Skype plugin disabled. So based on the descriptions, can you predict what should be the root cause? So that the support folks can actually focus on more important pressing issues instead of them manually labeling all of these and reporting out to management, let's say day in and day out. This is the classification model workflow which we followed. Started off with text normalization once we have the data, feature engineering where we extracted numeric features. Dimension reduction is again an optional step to prevent overfitting of models. And then the downstream machine learning applications, right, where we build supervised machine learning models and obviously evaluate the model, right, to test the performance. So as you can see, the workflow is pretty standard for most machine learning projects and even NLP projects. It's nothing different based on the standard workflow we talked about earlier. And these are some sample predictions. So we have just shown the short description here due to the visual constraints. Obviously, we can't put all the features here. But as you can see here, the actual reason and the predicted reason, it worked pretty well in many cases, as you can see, right? And obviously, it's not a perfect model, right? Accuracy can't be 100%. So in our case, we got around 80 to 85% accuracy, depending on the number of root causes we had. And automated incident resolution, this is pretty much the last industry use case I'll talk about. So the idea is we already built a classification model workflow, right, to predict the priority of the tickets or the root causes. So can we leverage those reusable components and build a new solution to basically predict what should be the knowledge article or the script which can be used to close a potential issue? So it can work in two ways. One is you build a supervised machine learning model where you already have past historical data of issues and potential solutions which were used to solve them. And you predict for future issue descriptions. And the other one is, like we talked about, information retrieval. If I enter a problem I'm facing, like let's say Skype not working, it works just like Google. It looks into similarity based features and it tries to find out the potential solutions which are most relevant to that problem, just like a chatbot or a search engine works. So the first scenario is pretty simple. We have the past historical incident data, which is our issue descriptions, let's say, and KB is the knowledge articles, which is the solution to close that ticket. And we built a recurrent neural network model here. And based on a future new incident description, we kind of predicted what should be the knowledge article used for resolving that ticket, right? And solving it automatically instead of someone manually sitting and looking through it. And the second scenario is the most interesting one, where we kind of built a search engine. You can think of it that way. So we had all the ServiceNow knowledge articles. ServiceNow is a tool pretty much which is used for incident management. And we built a ETL pipeline which parsed the data, pre-processed the data using all the text pre-processing steps we briefly described, and it dumped it into an Elasticsearch index. And then basically, once we got the knowledge articles, potentially we kind of correlated, right, that these issue descriptions were closed by these knowledge articles, and we had that mapping. So in the future, if someone enters some text like Skype is not working, we would basically convert that text data into potential numeric features like, let's say, word embeddings or document similarity features or TF-IDF, and we would kind of rank all the other documents which is in our Elasticsearch index based on their relevance, right? Like if Skype is not working, all the issues which were used to close Skype not working issues in the past, those would be ranked and showcased. Why we use Elasticsearch is Elasticsearch by default does a lot of this for you. So feel free to explore that framework. By default, it has a lot of capabilities related to document ranking, search, and so on. And we plugged in things like word embeddings and other stuff on top of that. That is why we used Python in combination with Elasticsearch. So this should give you a good idea about how you can potentially tap into the world of text data, right, and look into different types of downstream tasks like classification, clustering, document similarity, recommendations, sentiment analysis, and so on. And basically venture out now, maybe leverage some of these open source tools which I talked about. Feel free to check out my GitHub also and reuse them as needed. And basically think about solving some interesting problems in your own domain, be it research or in the industry, as you are going about your day-to-day job. So that is pretty much what I had to share. Thanks for having me here. Yeah.
Thanks, Dipanjan. Can we take 2 to 3 questions because people are really asking for it?
Yeah, sure. Absolutely.
Okay, so let me just go through that. Number one, the its question is, what is the model leveraged in chatbot?
Okay, so chatbot can be multiple aspects really. It is not like a specific model. You can have a combination of different models, but one of the most important things there is again relevance or intent, right? So some things can be like you can use a supervised learning model for intent classification, like whether the user wants to ask something, whether they want to get some specific information, whether they are just wanting to greet you and so on. So that part can be a supervised learning model. And then there can be, let's say, semantic similarity based models, where based on a question which you're asking, I will try to find out potential similar answers based on past historical searches or queries and so on, and give you back the answer. Other aspects can become more complex, like encoder decoder models, which are used in question answering systems, where I enter a question, it goes through the sequence of words in that question, and it outputs you an answer based on past historical data again. So basically, I would say a combination of supervised and unsupervised models would go into building a really good chatbot.
All right. The next question is, the examples are based in structured data. How to scrap and understand unstructured data?
Okay, so the idea here is we have like the examples I showed are mostly taken from data frames, right, which are CSV files. So definitely they are structured, though the text is unstructured. But if you really want to work with unstructured data from the web, you can look at APIs. Like let's say if you want to work with semi-structured data like JSON data, you can check out things like the Twitter API where you can get key value pairs and you can work off that, or you can even scrape websites, right? But I would be very careful when scraping websites because most of them don't allow you to do it for commercial purposes. So be very careful when you're doing that. But you can leverage frameworks like Scrapy and even Beautiful Soup, which you can just run on specific web pages. And you can even use the requests framework from Python and just get the web page as HTML and then extract the text content from there.
All right. The next question is, how NLP can be used for multi-label text classification?
Ah, absolutely. So multiple ways you can do it. Pretty much if you're using a deep learning model, you can just keep the last layer as a sigmoid layer instead of a softmax layer so that you can get probabilities for each of your outcomes, right? And it'll not just restrict it from 0 to 1, right? Like let's say if you have 5 labels, it'll not sum up to 1. Basically, each label itself will have a probability, and then you can just filter out and show the highest probabilities if you're using a deep learning model. And in general, what you can also do is you can use a one-hot encoding scheme where you can combine the different combinations like an NCR kind of a permutation. So if it is, let's say, a red vest, or let's say a red dress, or let's say a blue dress or a blue jeans, each of those combinations become one label. So it's like one-hot encoding. That is another approach where you one-hot encode the different combinations of labels, and potentially you try to predict them. So these would be the two approaches. Usually the sigmoid approach is the easiest, where you get a probability for each of your classes, and you can have high probabilities for multiple classes, which helps you do multi-label classification.
All right, let's take this as the last question. So here it is,
Sure.
how to continuously train the model with new samples.
Okay, so multiple approaches are here. This is like there are typically two, I would say, retraining policies. One is a batch-based retraining policy, and one is an online policy. So with regard to the batch-based policy, what happens is you already have a model, but you would need to retrain on the whole data plus new batches of data which come in. And another approach could be an online policy where as the data comes in, you keep retraining the model. That is known as online learning. Feel free to check that out. But it is very risky because if you don't have the right label data, your model may end up learning biased samples of data, which can be very, very risky. And typically, let's say in a deployment environment, what I would be doing is, if you are deploying, I would be using a container-based environment with something like Kubernetes, where one model is being served, and in the meanwhile, I can spin up another pod or something, and I update the model there, and then I start serving that once it's ready for deployment, and I just replace the other one. So that is another strategy from a deployment perspective, but feel free to check out online learning. That is where you do real-time updation of your model, but be very careful about it. Yeah.
All right, let's take one more question because there's this person, Mukil Dos, who has read your books and is asking you that how can we create an input for the deep learning model for custom named entity recognition, creating custom entity.
Creating custom entities, so I'm not really getting the full aspect of it, but maybe we can always connect offline. Feel free to reach out to me. But with regard to named entities, some of the things which we have looked into was generating custom features with regard to past historical data, and then feeding that into a deep learning model. So the first step with regard to any named entity recognition model, my mistake. The first step with regard to building any NER model is that you need to have historical data which already has your custom tags or your custom named entities, because otherwise your model will pretty much not work to the desired performance, or you can't even train an effective model. So that is the key. And then the feature engineering that can be customized depending on what you're doing. We have tried out different things like conditional random fields and other aspects. So we can always discuss offline. Like, I'm pretty much available on LinkedIn or even email or something. So feel free to reach out anytime.
All right, Dipanjan, thank you so much for this great presentation and the content which was used. I mean, it was superb, and I'm sure the audience have their own key takeaways, and it was really great from your side. Initially, we faced a technical glitch, but yeah, at the end, everything was all good. So, thank you, Dipanjan.
Yeah, no problem. Yeah, thanks for having me here, and really appreciate everyone who attended this. And thanks for staying through the technical glitches. It took off some time, but hopefully it was useful. Yep.
Yeah, absolutely it was. And tomorrow, for the audience, tomorrow we have another session at the same time on how to create a global product from India using AI to innovate mental health space. So same timings. Do join us. It is under the product management series. And thank you everyone for your time and efforts. And special thanks to Dipanjan. See you all of you tomorrow.
Thanks, guys. Bye.
Thank you.